Hi everyone, thanks for tuning in to my talk today. My name is Diana Blanco and I'm a first year astronomy and astrophysics graduate student at UC Santa Cruz. And today I'll be presenting the results of my work with Luca Ricci, my mentor and advisor during my time as an undergrad at CSUN, Mario Flock from the MPIA, and Neil Turner from JPL. So without any further ado, as we all probably know by now, over 5 years ago, this beautiful image of HL Tau hit the press, and it marked one of the key milestones and perhaps one of the largest steps forward in understanding how planets form. Over 5 years ago, I was just starting my last year of high school, and I knew absolutely nothing about protoplanetary disks or even exoplanets. But if I had seen this image then, I'd likely hypothesize that there's maybe something there carving out these dark arcs/rings. Could it be planets? I don't know. So in recent history, we've come quite a long way with our understanding of planet formation. So we know a nebula collapses into a disk, and within this disk, dust grains condense into planetesimals. Ultimately, the planetesimals combine into protoplanets, and finally, we get planets. But there's still some missing information about this step right here. Current modeling of protoplanetary disks, like the one by Flock et al. 2017, show that hydrodynamical instabilities, like the vertical shear instability, are responsible for these density structures within disks in which dust grains may potentially condense into larger and larger solids, and ultimately planetesimals. Since VSI has been shown to produce such structures, we used a VSI hydrodynamical simulation to model the dust and gas within a protoplanetary disk. Our results are based on the disk model 700 inner orbits after the beginning of the numerical simulation as prescribed by Flock et al. 2020A. The model itself spanned the 20 to 100 AU radial domain, since this is the region where VSI is known to develop. And the disk model itself included 3 bins of grain sizes. The first bin, the smallest bin, had grain sizes ranging from 0.1 to 10 micrometers. And this particular bin was very closely coupled to the gas. The other 2 bins had grain sizes of 100 micrometers and 1 millimeter, and naturally these weren't as well coupled to the gas. So we produced model images for the dust continuum emission at various disk inclinations and different wavelengths. This particular set of snapshots showcase the synthetic model image at 3 millimeters at the inclination specified. In the model images, we see some very encouraging features. There is a very clear localized region where dust is concentrated, a prominent dark gap located right outside this dust concentration. And in the face-on image, but even more so in the 45-degree inclination model, we see multiple concentric rings or arcs in the outer regions. For the purpose of this talk, I'll be focusing mostly on the face-on and 45-degree inclination cases, although I encourage everyone to eagerly anticipate the publication of the full results, which includes all of these inclinations. I'm sure we're all familiar with this image on the right by now, but ALMA, as part of the DSHARP program, has found striking evidence of local accumulations in protoplanetary disks. And more surprisingly, these local accumulations look exactly like those produced by our VSI hydrodynamical models. ALMA has done a tremendous service to the field of planet formation and will likely continue to yield fantastic results. So we decided to test ALMA's synergy with the future Next Generation Very Large Array, a project of the NRAO. When built at sub-millimeter to millimeter wavelengths, the NGVLA will be able to provide 10 times better sensitivity with baselines up to 60 times longer than ALMA. If all goes well, it's expected that it'll commence its early science projects in 2028, and it'll be fully operational by 2032. For our work, we quantified the potential of the combination of NGVLA and ALMA to observe substructures predicted by our models. And here are the results. At first glance, there are some very noticeable differences between the two image sets. Just for reference, above we have the ALMA image set, and down below we have the NGVLA image set. In the NGVLA image set, the dust concentration, inner ring, and dark or fainter gaps in the outer regions are incredibly well resolved, whereas they're not so well resolved in the ALMA image set. Due to its lower angular resolution, the dust concentration observed by ALMA actually appears to be attached to the inner bright ring. And also, due to the lower sensitivity of the NGVLA at longer wavelengths, with the exception of this bright inner ring of emission, not many of the disk features are observed at this wavelength. So let me quickly overlay the observational characteristics over this NGVLA at 1 centimeter image. So just for reference, this tiny white circle at the lower left corresponds to the angular resolution or restoring beam of each image. The most well-resolved NGVLA simulated observation, the NGVLA at 3 millimeter observation, had a synthesized beam corresponding to 8 milliarc seconds by 6 milliarc seconds, which is approximately 1.1 AU by 0.8 AU for a disk that's located 140 parsecs away. This beam is significantly smaller than the same observation by ALMA at the same wavelength. So here we have a panel of surface brightness radial profiles. Each of these correspond to a specific wavelength as indicated in the upper right-hand corner. And you'll notice that both the width and the depth of the gap vary with wavelength. At 0.87 millimeters, for example, it's a very shallow gap, while at 1 centimeter, it's a wide, deep gap. This wavelength dependence is primarily a result of the size-dependent coupling between dust grains and gas, since dust emission at different wavelengths is typically dominated by grains of different sizes. So larger gaps are more cleared out from the gap when compared to smaller grains. Another instance of wavelength dependence that we observed was at the local accumulation of dust. So this is at the weird azimuthal structure. So here we have a panel of azimuthal profiles at the radial location of the bump. One thing to note is that the relative contrast between the bump and surrounding emission varies with wavelength. At the case of the 0.87 millimeter image, the peak at the bump is 2.4, whereas the surrounding emission is only 2.0, 2.05. And over here at the 1 centimeter image, we have a peak at around 7, and the surrounding emission is around 3-ish. So that's a nearly 2 or 3-fold contrast. Also at increasing wavelengths, grains are more localized towards the center of the vortex region. So we see this narrowing feature in the azimuthal direction of these peaks. In order to compare our results with some of the DSHARP project results, we ran a simulated observation with ALMA at 1.3 millimeters that resulted in an RMS of 15 microjansky per beam and a resolution beam of 43 milliarc seconds by 28 milliarc seconds. Here, the dark gap and azimuthal bump are not very well resolved, and we don't see any hints of substructures in the outer regions. The fact that these features are buried by the high RMS noise of the observation suggests that some of these features may actually be hiding in current observations. Unveiling them would require observations with higher sensitivity and higher angular resolution. So we also investigated the potential of ALMA to observe these finer, low contrast features with longer integration times. We performed a simulated 40-hour ALMA observation at 1.3 millimeter for the 45-degree inclination case. The reason why we chose the 45-degree inclination case was because this showcased these outer arcs the best. The final RMS was 1.3 microjansky per beam, and the resolution beam was 18 milliarc seconds by 15 milliarc seconds. Here, while the azimuthal bump is not very well resolved nor well separated from the inner ring of dust, we can clearly observe the several arcs in the outer regions predicted by our VSI models. So to conclude, the NGVLA will revolutionize the field of planet formation, but it's still a long way ahead. ALMA at its current capabilities has already detected similar features like local concentrations and dark rings. Future observations with ALMA at longer integration times can reveal some of the more narrow features like arcs in the outer disk regions predicted by the vertical shear instability. Synergy between the two interferometers would allow us to detect disk substructures produced by the effects of VSI on dust grains of different sizes. So that is all. Thank you for listening. If you have any questions or would like to talk about my work further, please don't hesitate to reach out to me. I'm looking forward to speaking with you. Thank you. Bye-bye.